Hello students, Angus here, back for section 2 of our chapter 14, correlation and regression. Today we're going to cover 14.3, 4, and 5 at least, to help us interpret, calculate, and apply the Pearson correlation coefficient, as well as looking at other ways to measure correlation and test it. So, starting with this first slide, we're going to explore what we can use correlations for. And there are 4 things we can do with correlations, as listed in these points here. 1, we can predict outcomes. So, for example, if we know the correlation between 2 variables, let's say height and shoe size, so if someone is taller, we can predict that the person would have larger feet. In establishing a positive correlation, we can predict that as someone gets taller, their shoe size would be larger. So we can do this with correlation with 2 variables, as long as we find some correlation between them. We can also test the validity of something. It could be a test or a survey or some sort of measurement. And for example, if we have, let's say, the IELTS test, and the IELTS test is supposed to predict how well students do, let's say, in their courses, especially writing courses. So let's say, for example, you take the IELTS and score pretty well, and you go into, I don't know, English 110 and score well on that. So, lost track there. If you scored well in your IELTS, and it's supposed to predict how well you do in your courses, and you do well with your English 110 as well, let's say you got a 6.0 or 6.5, and you pass or do better than that on your English 110, then, there is a good chance that your IELTS test is valid, that, it's doing its job. It's testing what it's supposed to test, how well students would do in university classes, writing classes that is, and the test is, seeing whether students can and are ready to take those classes. Enough said about that. Next one. You can also test the reliability of, measures and tests too. Let's say you take the same test more than once. So for example, let's say you take this class and you did well on it, you wouldn't need to take it again. But, if the course does its job, teaches the students well, and, assesses their students well, it can be this class or any class. Let's say we'll just pick a random class here. I don't know, Psych 101. And you take it one term. Let's say it was winter this year. And you take it again. Spring. So we switch the scenario here. Let's say the student, doesn't have to be you, the student didn't do well in the winter term and, wants to take it again in the spring. Let's say the student didn't have time to prepare and learn from their experience and takes the same course again. A reliable course would show the same result for the student who is at the same level. So there would be sort of consistency and accuracy there. And in that case, there would be, correlation can be used to test that. If there's, no correlation between them, there's no difference between winter term Psych 101 and spring term Psych 101, then, it's good. This course is reliable. Finally, you can verify theories with correlation as well. Using correlation, you can, test whether your predictions work. So, for example, in one of the slides that talks about like churches, write this here, the number of churches and crime rate. Again, that's what's on the slide. It can be ice cream shops or whatever. And the theory goes, Well, if we have more churches, does that mean there's more crime? And again, correlation could verify that. If there is a positive correlation, you could say at least that there is a relationship between the two. As there are more churches in the city, the crime rate goes up too. It could be the more number of ice cream shops or ice cream sales, crime rate goes up too. So this leads to the next point. You can predict outcomes, you can test validity, you can test reliability, and you can verify theories. But one word of caution here leading to our next point. Correlation does not necessarily equal or demonstrate causation. So in the next slide, you're going to see an example of this, and we talked about this last time. So I can cover it again in brief if you forgot, or you can think through the example yourself if you remember, which is great. So the main point here is that while correlation can be used to make predictions, test validity and reliability, and verify theories, we cannot demonstrate cause of this. It is not the same as, let's say, a experimental design. It is not the same as, let's say, lab-controlled experiments. Correlation looks at the relationship between two variables and see what happens when they start to change. Do they change in the same direction or the opposite direction? So again, last time, correlation does not demonstrate causation. Okay? To establish causation, then, this is the next point, you need to do an experiment to see that when you change one variable, and this is the word here, manipulated, means to change, if one variable is changed, and this is your IV, your independent variable, and control all the other variables, that means don't do anything with them, whether the dependent variable is going to change. So again, we're testing the causal relationship between the independent variable with the dependent variable. If you remember, independent variable is the one that you manipulate or change, and dependent variable is the one that you would measure, okay, or count, to use a C word there. So the next example here, this is the last point in this slide. So the next example here shows you a case where you have a correlation, but you can't really establish or demonstrate causation with this. Here is the example. Again, the slide shows churches, but you can think of related examples if you want to think of something else. It could be ice cream sales. It could be beer if you drink. It could be swimming pools. Something that, people gather and engage in some sort of social activity. And then crime rate. Here it's a serious crimes. So looking at this scatter plot, you got your x-axis here and your y-axis, and you know where they increase and decrease. So here you can see as the number of churches go up, the number of serious crimes, or the crime rate, goes up also. And there's a sort of trend here that goes uphill. So this would have some sort of, positive relationship. Somewhere, I don't know, 7, 8-ish. Looking at how close the lines are. But at least we know for sure the direction is positive and the correlation magnitude is quite strong. Now, does that mean as the number of churches go up, ice cream, beer, pools, whatever, that just because ice cream goes up or churches go up and serious crime goes up, that building churches or selling ice cream or beer or building pools is going to create crime or cause serious crimes? Not necessarily. Remember, so correlation just looks at how two variables relate to each other and how they change in relation to each other. There are third factors, for example. So a third factor here, if you remember from your research methods class, if you can think of one, you can write it down or think about it. So a possible third factor could be temperature. Right? So the hotter the weather is, the nicer the weather is, the more people are going to go outside. For churches, it could be the number of people, right? This is an even more likely one. If there are more people in a city or country, then there are more people to commit crimes, if they choose to do so. So there are third factors that can explain the relationship between your first two, this here being churches and serious crimes, for example. So again, correlation does not necessarily demonstrate, and often do not, if not at all, causation. So, the next word of caution when it comes to using correlation deals with the technique itself and looking at the scores that you use, let's say in a scatter plot, to measure the correlation. So one point here to start off is that the correlation coefficient value, or the magnitude of the correlation, can be affected by the data itself. And we'll see this in the next slide. Something to think about. So the points on the scatter plot, to put this in another way, the points on the scatter plot changes the magnitude or the size of the correlation coefficient. So if you remember these shapes that we had, whether it's a straight line or whether they're like a kind of a sausage oval shape or they're all over the place like a cookie shape, the points on the scatter plot changes the correlation coefficient. It can make it stronger or weaker depending on where the points are. If you happen to restrict the range of your calculation, if you happen to not include all the points, let's say, and you can see this clearly on the next slide, if you include only some of the points and not all, this means, this is the part where we say severely restricted range here, then you're going to get a very different correlation coefficient than if you were to use more of the scores, and technically you should use all of them. So this applies to samples. Remember, this is a case of population and sample and how much data you have. With population, you get all of the data. So, the population could look something like this, a fairly weak correlation. If you happen to grab only a sample of this and put this in the scatter plot, while the population could show a, moderately strong positive correlation, your sample scatter plot, when you grab from, only a range of the scores and, not do the whole random assignment and random sampling, then you could get, for example, a very different correlation where right now this looks more like a cookie, so it's a lot weaker. It could be close to 0. Whereas this one is somewhere along the range, I don't know, looks pretty strong, positive, 0.56-ish. And the next slide gives you a clear picture of this. This is an example of what we just talked about, but enlarged. Here we see how restricting the score range, and this can be done with sampling, that is not randomized sampling, or somehow only choosing to include certain points in a restricted range to measure your correlation. You can see here, if you get everyone's scores, you can see an upward trend and a fairly strong positive correlation. Again, this might be along the lines of, I use the approximate symbol here, 0.56-ish. And here, we only use a range of it. This can be any range, really. Like this, that works too. Or this. This is slightly better because, it looks like a positive trend. But I'll erase these parts here and go back to the first range. This one shows it the most clearly for our case here. If you only use this area and restrict your values to a limited range, here is you restrict your x values, then you're going to get a very different correlation coefficient. It may not change the direction, but it will certainly change its magnitude or strength. oftentimes weaker because you're only grabbing a portion of everybody. So, another case, in addition to restricting the range of your x values when you measure correlation to change the correlation coefficient intentionally or unintentionally, is to introduce outliers. So you could take away previous scores, ranges of scores to change the correlation coefficient. You can also introduce extreme scores, outliers. Outliers here means extreme scores. It could be extremely high or extremely low. Okay? It could be high or low. And when you do this, here extremely deviant means different. In the case of farther away from the mean. And when that happens, oops, let's go back. When the score is much larger or smaller than the others in the sample, in your scatter plot, you're going to shift the direction and maybe even the magnitude of your correlation because you're changing the shape of the scatter plot. So this is the last point. When you introduce outliers, or when your sample somehow includes an outlier, and sometimes this is out of our control. It could be like somebody who's extra smart in the class, or somebody who is really struggling in the class. It could be something that has a really different score than somebody else. And when that's introduced, that can change our measure of the correlation coefficient. So this is why the last point says, outliers produce a disproportionately large impact on the correlation coefficient. So that's what the words say in this slide. Here, the next slide show you what that means. Take a look at this first picture here. So we'll call this A and this B. So with this first picture here, you got, again, a kind of a cookie situation. They've measured it, and you can try this too. One thing you can do is, since you got your data right here, you can try calculating your R to see if you get the same result. So this is x times y, and then x times y squared. And so this could be like 3, 15, 24, 4. Okay. 10, and then you square these, 225, 24 times 24, I can't think of that one right now. Okay. And, get your this, get your that. Sigma x, sigma y, sigma xy squared. Whatever you need to calculate your R. So you can go back to that as well. And that's something you can do with these slides that you probably wouldn't think of at first. So again, to review, not to go back on the tangent here. So if you wanted to do this, you're going to need your sum of products, and you're going to need your sigma xy, which you can do. You don't need to square it like I did. But again, the formula is right here that you could use to get your sum of products and get your sum of squares and calculate your R. Let's go back. Anyway, so you got A and B. Again, you can calculate your R if you need to. X, Y, and you can do this twice and see for yourself, and this practice for your test to calculate correlation coefficients. Anyway, here is sample A, and sample A has 5 scores, X's and Y's, and put them in the scatter plot, and it shows a very weak negative correlation, which again looks like a cookie. But as soon as we introduce this outlier right here, in this case, it's an extremely high score, an extremely high X value, and an extremely high Y value. So here it's 14, 12, X and Y. In this case, XFYF. When that happens, now you introduce an upward trend that wasn't there before. And the outlier is the cause of this. We changed the correlation from a weak, very weak, close to zero, negative correlation to a very strong, positive, close to 1 correlation coefficient. So that's what outliers can do. So again, to review, you can change the correlation coefficient intentionally or unintentionally by 1, restricting your score range in the scatter plot when you make your calculation, or introduce an outlier that wasn't there before and change both the direction and magnitude of your correlation. Oftentimes, it will make the correlation much stronger than it looks, or much stronger than it is, without the outlier. So those are words of caution. Other words of caution when you do work with correlations and correlation coefficient are some conceptual warnings or concept reminders. So we talked about the first point before. A correlation coefficient has a scale from 0 to 1. If we use R, for example, the weakest is 0 because there's no correlation. The strongest can be in either direction, positive 1 or negative 1. In terms of the coefficient value, you cannot have something that is larger than 1.00000, so it cannot be something like this. No, you can't. It cannot be smaller than negative 1 either. No. So the weakest or no correlation is 0, and the strongest is 1. Strongest negative is negative 1. Strongest positive is positive 1. That's number 1. Caution reminder number 1. 2. Because we're working with decimal points when we're calculating R, in this case the Pearson product moment correlation coefficient, or just Pearson correlation coefficient, that number, especially when you see decimal points and it's between 0 and 1, it looks like a percentage or proportion, but it's not. Do not for correlation, not for R, not R squared, not for R. R is not a percentage or a proportion. It is not a percentage or a proportion. Think of it as more like a slope. The M in your mx plus b. Although that's not quite it either. But the main point here is to say that R, your correlation coefficient, is not a percentage or proportion, even though it looks like it's between 0 and 1 in terms of absolute value. Instead, R squared, when you square the correlation coefficient, okay, squared correlation, that is your, and this is a familiar term, proportion of shared variability. And you may have heard of this term before in your ANOVA or your T as proportion of variance explained. Again, we square that correlation coefficient to get a square correlation, which here reads as the proportion of shared variability. That is a proportion. There are ways to explain this, but for now, in this class, at this time, at this level, remember 2 things. 1, R, your correlation coefficient by itself, not squared, to the power of 1, is not a percentage. It is just the correlation coefficient. Yes, it is between negative 1 and 1, 0 being the weakest, but it is not a proportion or percent. When you square R, then it is a percentage. Then it's a squared correlation, and it is read as the proportion of shared variability, and it is also called the correlation of determination, which for now you can read it as the proportion of shared variability explained. Okay, and we'll show you what that means. Here is a simple demonstration of this. All right, it's working again. So the correlation or the coefficient of determination, which is your proportion or percentage of shared variability, and this is shared variability between x and y, by the way. And don't think of this as a denominator, so I'll just do that. There you go. Is r squared. So this is your squared correlation. Okay, so in your work, your practice sheet, and your tests, and when you do research with correlation, yes, you do need to calculate your correlation coefficient first, and that's R. Correlation coefficient. Okay, you do this for coefficients. For linear data, for interval ratio scale, like both variables are interval ratio, like time and age, height and shoe size. So you want to measure the relationship between those variables, those kinds of variables. Yes, you would use something like Pearson correlation coefficient, R. And when you do R, yes, you do that. And then if you want to figure out the percentage of shared variability, square that correlation. Squared correlation. Okay, so that's one demonstration of this. Here's how we would do it. So again, this picture shows 3 degrees of linear relationships. Here, for example, we have shoe size and IQ. It can be height and shoe size. But here, you wouldn't really see a strong positive correlation between the size of a person and quote-unquote the size of their brain, or IQ, measure of intelligence. You may remember this from your Psych 101 or 102 class, or at least your Intro to Psych class, depending on where you took your Intro Psych class. So again, it's a weak correlation. It looks kind of positive, but the points are everywhere. Positive something pretty weak, maybe 7. And then, just for math's sake, I'm going to do it like this. It's going to be easier. So R here, IQ scores and college GPA. This one makes a bit more sense. So if a person has been measured, quote unquote, to be smarter with IQ tests, and they go to college and they get, tested and take courses and have their GPAs. And here you see, okay, a quote unquote smarter person with a higher IQ tends to do better at school or college, then you're going to get a fairly strong correlation. Let's say 0.6. Okay. Finally, is a really obvious one when you look at it. A person's salary per year and then a person's salary per month. Obviously, if you get a higher annual salary, when you get to a stage in your work where your salary is, given to you by the year, they go, oh, okay, you get $30,000 a year, $40,000 a year, $50,000 a year. You still get paid by the month, so your monthly salary also increases proportionally. So for example, if you are, getting a $48,000 per year salary, every month instead of 12 months in the year, you would get $4,000 per month. If you bump that up to $60,000 per year, then your monthly salary gets bumped up to $5,000 a month. So here, you're going to get a perfectly linear positive correlation. Here you get 1. Positive 1. No doubt there. It's just straight out math. When you do your R squared to measure your proportion of shared variability, or your coefficient of determination, we'll go backwards here. Looking at 1. So R squared here, 1 squared is 1. So because it's a perfect positive correlation, as in it's strong as it can get, 1, positive 1, then yeah, the variability in annual salary explains the variability in your monthly salary. And how they covariate, their covariance or covariability explains how they both change. As one goes up by 1 point, the other one goes up by 1 point. So when you square that value, you still get 1. Here, let's say with IQ scores and college GPA, the correlation coefficient R looks pretty strong, 0.6, pretty strong. You square that, then it becomes 6 squared. Let me see if I did my math here correctly here. 6 times 6 is 36, 0.36. So here would be 36% of the shared variability between college GPA and IQ scores explains, how these variables change. There could be other factors outside of, the correlation between college GPA and IQ scores and how they work. So maybe there are some people here that, have high IQs but didn't do so well. Over here, high IQ but didn't do so well. And somebody with lower IQ but did much better, if not the same. And finally, shoe size. So again, R here is plus 0.1. I put 0.1 so it's easier to calculate. You square that, 0.1 squared, well, that's 0.01. So that means 1% of the shared variability explains how shoe size and IQ affect each other. So as you can see here, again, I use 0.1 just to make calculations simpler. It could be 0.2 and then you'd get, 0.04, which is 4%. But again, when you square the correlation coefficient, you get your coefficient of determination, which is your percentage of shared variability. Again, the stronger the correlation, the stronger your coefficient of determination, but it is by the power of 2, which is you square R. So the next bit now, we're on 14.4. Hypothesis testing with the Pearson correlation. Just like we do hypothesis testing with mean differences and comparing variances, we also can and need to do hypothesis testing with correlation. In this case, we're doing hypothesis testing with the Pearson correlation. And as usual, because we don't really have access to population data most of the time, in fact, not really, unless you happen to be working with small population groups, when we test correlation, we also work with sample data. And because we're working with sample data, we must use inferential statistics. We cannot just say based on the sample whether the population or our target population is going to be positively or negatively correlated or if there's any relationship at all. We must test it. We must use inferential statistics. In this case, we need to estimate our population correlation coefficient, and we use the Greek letter rho. And this time it is rho. Remember, so in ANOVA, we use this, and this is eta. Okay. This P-looking Greek letter is actually rho, and we use this for population correlation. Okay. And your hypotheses are, very familiar if you think back to how hypothesis testing works. So, for example, if we say the null hypothesis, which means no direction, no relation, for non-directional tests, we go, oh, okay. We say there is no correlation between the, variable A and variable B in the population. So rho is 0. Okay, and the alternative hypothesis here, which is written as H1 here, it could be HA or whatever. The alternative hypothesis would be not equal to 0. It could be positive correlation or negative correlation, either one, but the alternative says there is some kind of correlation. If we go directional, think back to your T and Z test. We start with the alternative hypothesis first. The directional is determined by your research question, your research hypothesis, your alternative hypothesis determines what direction you use. So if you predict, or if you want to test whether there is a positive correlation, then we list or write our alternative hypothesis H1 or HA here as rho, looks like P, I know, is greater than 0. And then your null hypothesis is the opposite of that. It can be no correlation, rho equals 0 or less than 0. When you do tests in the opposite direction, here it's the positive correlation, negative correlation. Your research question, your research hypothesis, alternative hypothesis would say rho is less than 0 because we're trying to test for a negative correlation. And our null hypothesis, again, the opposite of this, is that rho is equal to 0 or greater than 0. So that would be your step 1 in hypothesis testing. Again, the reason why we use inferential statistics may bring you back to the whole idea of restrictive range as a caution, like, hey, if you just grab sample data, you're not grabbing everybody, you could change your correlation coefficient, which would no longer be representative of the population. So here, look at this. Even if we use random assignment and random sampling, we can still grab, fairly representative sample of the population. But again, we're not grabbing everybody. Let's say we only grab 4 out of, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 20. Okay, let's say 1/5, 4 out of 20 people. And we grab them, and yeah, it looks kind of representative, but we're not grabbing everybody, and we're still going to get sample error and sample bias and so on. And then we need to use inferential statistics. We still need to test the hypothesis of this. Okay. In this case, we're testing for correlation. And this is what the test would look like. The steps are the same. If you remember the steps, step 1, state hypotheses. Step 2, pick your tool, or at least as you pick your tool of testing, T or Z. You would set your critical regions and decision range. Step 3, collect data and get test statistic from your observed data. Step 4, make your decision. And step 5, which is to interpret that decision. Okay, so the steps are the same as before. We use a same tool that we've used before, but now we're testing correlation using sample correlation R. So we can calculate the sample correlation, we can calculate sample R, and we're going to test that whether that is far enough away from your population correlation coefficient, rho, which would be here 0, like all the time. Again, you would check back on your null hypothesis for this, but when you test it, it would be 0 here. And then it will be some value here for R. And then you're trying to see, again, just like the same principle for T and Z scores, you're trying to see if that difference, if that test statistic is far enough away from your population coefficient to say, yeah, there is a correlation of some kind, positive or negative, or just some kind of correlation. Okay, so the formula is there in concept, and you can use T or F for this, and we only show T for this chapter because, we're working with two variables, and because we're only comparing, just those two variables, and we're doing the correlation of two variables, we don't need to use ANOVA to avoid experiment-wise alpha going up as we add more pairwise comparisons. One thing to note here as you conduct your t-test, again, because we're using samples and we don't know the population standard deviation, at least, or even the population mean, that we use t-test and are going to need degrees of freedom. Now, remember, because we're looking at two variables, even though it's the same number of people, think repeated measures or related measures tests. So it's not n-1, it's n-2, one for each variable. And that's included here. This is your degrees of freedom. This is your 1 minus coefficient of determination. And you square root that to measure in quote-unquote standard deviations or standard error how far your sample correlation is away from your test population coefficient, which for the null hypothesis, assuming that is true, is 0. Okay? So here's what it would look like once you've tested this. So if you got, a t-value, you set a critical region somewhere with, with the right degrees of freedom, and you can try this in your worksheets, on your exercises, and you find a quote-unquote significant result where your test statistic, your t observed, is greater than your critical t in the right degrees of freedom, looking at the sample size, and then -2, and then getting the right, sample data, getting the right R, which you can calculate using the sum of products divided by your sum of squares, x and y, and square root that. Go back to you can refer to your formulas for this and practice with them. Then you would include the various things. The value of the correlation, that's your R, and this is your sample R here. Remember, R, this is sample, not population. Sample. So again, sample correlation is R. Population correlation is the Greek letter rho, which looks like the letter T. P, rho. Okay. You would include the sample size, from which you'll get the degrees of freedom. Again, degrees of freedom here would be n-2. Your p-value level, again, this is the part where I would caution you. If you use some kind of software or program, whether it be online or purchased, like SPSS, for example, or some website, you can Google what SPSS stands for. And so if you do that and get some p observed, great. The computer's done the work for you, and yes, you can make a decision, and it will probably be right because, as long as you put in the right numbers, yes, the computer does what it's supposed to do, the program does what it should, and gives you the right, test statistic and help you make at least the right decision. However, that does not mean you've done any of the work at all, necessarily. We are looking for values like critical values and observed values. So we must see in your work, and you must practice, and I strongly recommend this so you know how you get these p-values. Your observed value, which is your test statistic. I won't use the line so it won't look like a fraction. And then here is your critical value. Again, if you have a observed value which is more extreme than your critical value, then yeah, you would reject no. If it is less extreme, then no, you would fail to reject. So that's what the P means. The P here is P observed, the observed probability. The area under the curve in, let's say here, because we're using a t-test, your t distribution. So, somewhere over here, and you got, let's say this is your critical value, and you got your observed value. And so there's less of an area under the curve. So this is your P observed over here, the area itself. The point in which on the distribution on the x-axis, that's your critical t value. in the t-table. And you're measuring here, and you also tell the reader and yourself what directional test you use, whether it's non-directional or two tails, which, if you remember, for two-tail test, your alpha for each tail is divided by 2 for each tail. So just a couple things to remember. Here we're giving you the word point-by-point form for you to practice. Here we're assuming that you've done enough t-tests, z-tests, f-tests, that is, independent samples testing, ANOVA, and inferential statistics, that you can follow these directions and do them. If not, you can go back to your samples, t-tests, your z-tests if you got to, and practice those tests first. Remember those steps. They're the same steps that you use to calculate, or in this case, figure out, test your hypothesis whether their two variables do correlate in the population. One thing I'm showing you here, but we will not cover in this course, is the case of partial correlation. So this is the case where there could be some third factor. In this case is Z. Here is the possible third factor. And remember we talked about that correlation does not necessarily equal causation. In fact, that's like rarely, if ever, the case, because we can't demonstrate causation with just correlation alone. So partial correlation is a way to measure the relationship between two variables, and as the point says here, while controlling with math, in this case, the influence of a third variable by holding it constant. So let's say, for example, our number of churches and crime rate. We're going to use one of the more likely third factors, let's say here for Z being the number of people. If there are more people, you probably would have more churches. However, it is also possible that with the same number of people, you could have more churches being built. Just like in the same number of people, you could have more ice cream shops. Let's say more people want to go into the ice cream business, seeing how lucrative it is in summer or something. If we control the number of people as a third factor and test again the correlation between the number of churches and crime rate, and we get a similar R, having controlled that third variable and by holding it constant, in this case being the number of people in the city or country or whatever, using a formula like this that includes the correlation coefficients of interaction between the variables x, y, and z, then if, let's say, R were, here, x, y were to be equal or very close to a partial correlation, then yeah, you would say even after controlling the third variable, you can now say with more evidence, statistical evidence, that yeah, the variables x and y, it could be crime rate and number of churches, are positively correlated, even controlling a third factor, fourth third factor like the number of people in the city. Here is what it would look like in a graph. So again, the number of churches here, the number of crimes here, and now we try to control the third variable here, in this case, as we have mentioned, the number of people. Again, the more people there are, the larger the cities would be. And having controlled the third variable and still seeing a positive correlation, we can say, even in a partial correlation, that yes, the number of churches, let's say here x, and the number of crimes, the crime rate being y, is positively correlated. Last bit here before we finish for this part is looking at alternatives to the Pearson correlation. Now, so far we've been working with interval or ratio scales when we look at variables. Again, the number of something could be number of churches, number of crimes, height, IQ, temperature, whatever. They have some numbers attached to them. And it's on a scale, interval or ratio. What would happen if we start using other scales, like nominal or ordinal scales? Or what if we're not finding or looking for a linear relationship. So Pearson, as the point says here, works for linear relationships. Same stuff that you learn from your slope formula. Again, linear relationship. As one variable goes up, the other one goes up or it goes down. So you have a positive or negative correlation or no correlation or it's all over the place. Again, any correlation would be linear, straight line. And we use these for ratio or interval scales. Could be degrees, temperature, IQ, number, whatever. For other correlations, those exist too, we need other coefficients. So, for example, we could have a nonlinear relationship. It could be a curve. An exponential curve going up. The curve going in the opposite direction, kind of like a square root curve. Okay. It could even go like this. A parabola. A U-shape. It could even be upside down U if you wanted to. Which I ran out of space. But none of these are straight lines. And sometimes we're using other scales. So it could be nominal, like, I'll use color here. It could be red, blue, green, not ranked. And then ordinal, it could be, I don't know, your grade letters, letter grades, A, B, C, D, and so on. Okay. So again, the Pearson correlation works for linear relationships, straight lines, up or down, when we measure interval or ratio scales with two variables. Other correlations that we can measure, we would measure those and use the different correlation coefficients for linear relationships, which are curves. And we use different measure scales like nominal, for example, colors, or ordinal, ranked categories like letter grades. We'll show one for this course, and this is one where we'll practice and it's covered for your course and tests. So just in case at this point you're wondering, hey, we're introducing more correlation coefficients. Which one are we going to use? We are going to use the Pearson one for linear relationships, for interval or ratio scales. That's your R, by the way. And Spearman correlation coefficient for ordinal scales. Here, ranks. This one, both of these will be covered in your course, practice in your worksheet, and assessed in your tests. So right now we're showing you the Spearman. Even I get confused. Spearman correlation coefficient for ordinal scale or ranks. So sometimes you can get both variables measured in an ordinal scale. They're ranked somehow. Or sometimes you can get interval or ratio scores, but you're not getting a linear relationship. It could be some sort of curvilinear relationship like this. Okay? Those are the cases where we use the Spearman correlation. Here is a case of this. And this, we start with the nonlinear positive relationship. So here's an example. X is amount of practice. The more you practice, the better you perform. X and Y. However, there is a special property of this relationship here. Yes, at the beginning, if you have no practice and if you practice even a little bit, you're going to get massive gains in performance. But as you practice enough and start to master what it is you're supposed to do, it could be statistics, it could be writing, it could be drawing, anything that requires some sort of skill, and that is honed by practice. The higher level you go, the better you perform. As you add in more practice, the less the gain you're going to get. In economics, there's a law called the law of diminishing marginal returns, or something like that. So again, here is that the curvilinear relationship. Yes, you do get a positive correlation between practice and performance, but as you accumulate more practice, the gains in performance decreases. So it's not a straight line anymore. So again, your relationship coefficient, if you only use Pearson, since you got dots over here, if you were to test it for a linear relationship, the coefficient would be weaker because the dots on the actual line show, while it shows a curve, a curvilinear relationship, they are deviating away from a linear regression, a straight line regression line. So these points are away. So therefore, as you know, if the points on a scatter plot are farther away from a regression line, this is the regression line, which we're going to measure next time, the weaker the correlation coefficient. However, if we were to test for a curvilinear relationship, that itself is not covered in this class. For now, we're going to use ranks instead to test for a causative correlation using ranks. Then we'll get a more accurate correlation coefficient than we would normally get if we were to use Pearson R for a curvilinear relationship. Here is a side-by-side comparison of this. Again, we see a type of curvilinear relationship. It could be practice and performance. So a way to solve for the discrepancy in getting a weaker R, if we use Pearson, a straight line test for correlation, first we rank the scores. By ranking them, now we eliminate the curve, quote unquote. So here you can see that in the first picture, on the first half on the left here, these are individual scores scored in X and Y. Now, if we were to simply rank them instead of measure them on an interval scale, notice these scales here are ratio scales because it has 0. And so now instead of a ratio scale, not ration, ratio, here we use an ordinal scale, ranks, ordinal. These are ranks. Notice here, instead of a curve, now you got a straight line. And because we got a straight line with ranks and not ordinal scales or numbers, straight up ratio numbers, then we can measure the correlation more accurately using the Spearman R. So let me see here. Here is the Spearman correlation coefficient. And I'm going to demonstrate this to you with a worksheet. But before we do that, here are some words of caution for Spearman correlation when you get tied ranks, or when you get scores that are tied and you got to rank those guys. Here's what the points say. If you got tied scores, then the tied scores still need ranks. So it could be like X, Y here. You got somebody who is clearly got high scores, and then you got two people getting the same score somehow. So you get tied scores. How are you gonna rank these guys? Well, here you'll list the scores in order from smallest to largest, and we got a practice of that in the worksheet. Okay, and then you assign a rank to each position in the list. So here would be rank number 1, rank number 2, and rank number 3, smallest to largest. When 2 or more scores are tied, compute the mean of their ranked position and assign the mean value to the rank of each score, to the final rank of each score. That is each of those scores. So here in this case, 1 plus 2, divided by 2 is like 1.5. So then these become 1.5. It's 1.5, like that. We would not really test for this, but you can practice it just to see how this would work. But here is a demonstration now. Using the formula for the Spearman correlation, we're going to turn the ranks into simple integers. And you can simplify the calculations, and the D here, D stands for the difference in the ranks between X and Y. And when you do the table itself will be ranks. So I'll show you that in a minute. And then once you've done that, then you can calculate your R Spearman or RS statistic using this formula. So what we're going to do is, I'll get a worksheet here. So I'm going to do this side by side with the formula on the right and the worksheet on the left. As you watch this video, what I recommend for a moment is you write down the question and the formula on a piece of paper, because right now things are much smaller on the screen even if you go full screen. Then follow along using the data from your practice sheet and do your calculations with your formula sheet and applying the concepts used for Spearman correlation. Here we go. So let's try this here. Question 11 on the practice sheet. You got the following scores here: 4, 5, 5, 6, 6, 6, 7, 8, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9 scores. So you'd rank the scores from smallest to largest that we've done. And we figure out, okay, well, these are tied ranks. Well, what rank is the score 7? Okay, so here you got 1, 2, 3, 4, 5, 6, 7. So take a moment and see what rank you would assign this to be. Okay, now, yes, we did talk about tied ranks. So if you thought, okay, well, here's 1, 2, 3, 4. It's not right, but we understand why. Because there's 2 5s, that's 1 rank, and that looks like 1 rank, and 3 6s, that looks like another rank. But remember, when we do tied ranks, we actually include them and calculate the means of those ranks and put the mean values. So here, for example, the 2 5s, yeah, they'll still be 2 because 2 plus 2 is 4 divided by 2 is 4. So they'll still get 2. Here's what's interesting though, but no, actually, correction. It's 2 and 3, and so here there'll be 2.5 and 2.5. Here you got a more interesting one. You got 4, 5, and 6. So 4 plus 5 plus 6 is 15 divided by 3. So these would be 5, really. 5, 5, 5. And then you count 1, 2, 3, 4, 5, 6, 7. And so it's still rank 7. So the score 7 itself technically has a rank of rank 7. So that could be on the test. So make sure you watch out for that. The tied ranks though, what you do is you rank the scores normally from left to right. The one on the left would be 1, the next one would be 2, the next one would be 3, and so on. And if you got tied ranks, you would add up the numbers of the same score, add up those ranks, find the average of those ranks. So here, for example, 2 and 3 would have an average of 2.5. 4, 5, and 6 would have an average of 5. And then you move on to the next one. In number, it's 7, and then 8, and 9. Okay. Now, number 12 is the important one. We're going to calculate the Spearman correlation for this set of ranked data. And these scores, by the way, are ranks, not numbers anymore. So that's our first step done. Once you've coded the scores into ranks, you have the ranks here. So here in the first person, for example, A, B, C, D, E. The first person, A, was ranked number 1. Having the smallest score in X, but the fourth largest score in Y. Person B has the second smallest score, second ranked in X, but the fifth or the largest score in Y, and so on. These are ranks, by the way. So using the ranks, now we can calculate D, and of course D squared. So here we got, and we do the difference in ranks here, we're calculating D. 1 minus 4, which is negative 3. Here's 2 minus 5, which is negative 3 again. 3 minus 2, which is 1. 4 minus 3, which is 1. Whoops, I wrote the equal sign for that. 5 minus 1, or the fifth rank minus the first rank, equals 4. So you square these values here. I'm going to do this. Negative 3 squared is 9. Negative 3 squared again is 9. 1 squared is 1. 1 squared is 1. 4 squared is 16. Add those up to get your sigma d squared, which is 36. 9 plus 1 is 10. 9 plus 1 is 10 again. 20 plus 16, that's 36. So this is our sigma d squared equals 36. And then you basically have everything you need. So my Spearman correlation coefficient then, using the formula and getting my scores ranked first, coding those scores in ranks, and then getting the difference in ranks in D, squaring those, adding those up, you'd get 6 times 36. I calculated D squared already. And then I plug in your N, which here is 5. N squared is 25 minus 1. Again, we rank them. It's similar to degrees of freedom in concept. So once we're done, here's what the formula would look like. And we plug the numbers in. And we get 6 times 36. Okay. You can take a moment to calculate this if you want. Okay, 216. Yeah, so that's, 180 plus 36, 216. Anyway, 216 divided by 5 over 24. Again, so 1 minus 216 over 120. And so 216 over 120. Oh, let me give more room here. So we're doing this last bit now. 120. So here's 120. And then here you got your point. 960, and that's 8. 960, so that works out. So here you have 1 minus 1.8. And then so 1 minus 1.8 would yield you 0.8 negative. Negative 0.8. And you can get that right there. That is your Spearman correlation. So looking at this, and you can just double check quickly with your data. Look at this. So as the ranks go up from A to E in your X column, as the person scores higher in X, yeah, you're going to see the person scoring lower in Y. So you still get your 4, 5, and 2, 3 over here. Yes, they're a little bit mixed up. Your 4 and 5 is switched, and your 2 and 3 is switched. But here you can see that, yeah, the highest ranking X score for person E gives the same person a lowest rank Y score. Okay, so it shows a strong negative correlation coefficient with your Spearman R, which reads as RS. There are 2 other correlation coefficients that you would use. We will not cover them in this class in terms of how to calculate them, but we will show you why they're there and what they're used for. First, the Point-Biserial correlation is like your t-test. And we still code our variables as 0 and 1 for our Y scores. And we are still trying to find some difference between the means. But we use it when we want to measure the correlation instead of the differences. Again, we still use R squared for effect size. Again, we use these the same way as we would do an independent samples t-test. But instead of trying to look for the difference, we're trying to see if there's a correlation between two variables when we just only measured with a 1 in one scale. But we code the variables as 0 and 1 in the y-scores. Here's another one. Your phi coefficient. We use these when both variables are dichotomous. So, for example, you could be a male or female by gender, for example. If we only use those two genders, and we go, oh, the person answers yes or no to a question. It could be like, oh, do you, this is harder than I thought. Let's say, do you, I don't know, wear a dress or something. Anyway, it's harder than I thought, trying to stay politically correct. But anyway, dichotomous variables. It could be male, female, yes, no, pass, fail. Here's a better example. Whether you are a college student or university student, again, dichotomous. And whether you're going to pass or fail a class. Okay? Again, this is used for cases when the variables are dichotomous. That's only two outcomes. You would code the outcomes as 0 and 1, similar to your Point-Biserial. And you would use the Pearson formula to calculate R, as you would. But again, we would use this for dichotomous variables, and we would call this the phi coefficient. Here we use your R squared, your coefficient of determination, to measure effect size also. Again, this reads here the proportional variability in one score that is predicted by the other. So again, depending on the scale that you use when you measure your variables, whether they're interval, ratio, ordinal, or nominal, or they're dichotomous, or what kind of relationship you're looking for, linear or curvilinear, could be nonlinear, you would use a different correlation coefficient. Before we do our learning check, I will tell you one last time that in our tests, we're going to test you on your Pearson correlation, which is your linear relationship on interval and ratio scales. So let's think up, down here. And we would test you on your Spearman correlation, which is for ordinal scales or ranks. Okay, so I just write ranks here so you can help remember. So, having said that, this will conclude our section 2 of chapter 14, where we do hypothesis testing for your Pearson correlation coefficient, as well as introducing how you can calculate your Pearson correlation as well as your Spearman correlation. So let's do these checks to finish things off. Question 3 in our lecture slide this time. Participants are classified as morning people or evening people. Then measured in a 50-point conscientiousness scale. Which of these correlations would be used to measure the relationship? So take a moment. You can pause this video and think about it. Again, there are two groups of participants, morning people, evening people, two samples, and they're all measured in one scale. Independent samples on one scale. One variable. But two groups. Is it the Spearman, the Pearson, Point-Biserial, or phi coefficient? If you said Point-Biserial, you are right. Again, not all variables are dichotomous here. This conscientiousness scale is 50 points. It could be interval if it doesn't have a 0. It could be ratio if it does have a 0. Strange that person would be 0 in conscientiousness, but who knows? There is a morning or evening people that would be nominal. It could be dichotomous. So because not both variables are dichotomous, we would go with our Point-Biserial, just like we would compare two samples, here being morning people and evening people. This is the correlation we would use to see if there's a relationship between, whether a person is a morning person or an evening person, and more how conscientious they are. You might predict like, oh, if they're morning people, they're more conscientious, maybe. Or you could say the other way around. But again, you would use the point-Biserial correlation to test this. 2 more learning checks and then we're done. I'm running out of saliva too. Okay, question 4, 2 parts. A, the Pearson correlation is used with dichotomous data. Sorry, I keep reading these wrong. The Spearman correlation is used with dichotomous data. Spearman. True or false? And B, in a non-directional significance test, non-directional, the null hypothesis here is going to say that the population correlation is 0. Again, non-directional significance test, could be a T test, and the null hypothesis, your H0 or H0, states that the population correlation coefficient, rho, is 0. True or false? Take a moment, think about it, write down your answer, think your answer, and check. So, for A, if you think, oh, wait a minute, the Spearman correlation, that's not used for dichotomous data, that's used for ranked data, then you are correct, as it says on the slide. For dichotomous data, which one do you think it would be? See if you can figure it out by now. And yep, you would use, for dichotomous data, for both variables, you would use your phi coefficient. Again, that's your yes, no, college, university, pass, fail, male, female, something, dichotomous variables. And for your non-directional test, remember this one, you're looking for either or, it could be positive or negative correlation, but the no difference here, no correlation, means rho is 0. And for your alternative hypothesis, as you can probably guess, rho is not equal to 0. I'll write rho properly. Again, for your directional test, you can have right-tailed test, right-tailed. You can remember this one. Rho is greater than 0. That's your alternative. And then, for your null here would be the opposite direction. Like that, less than or greater or equal to 0. And if it's a left-tailed, again, looking for the negative correlation, then rho is less than 0, and then here the left-tailed alternative null hypothesis would be greater than or equal to 0. Okay. So that's it. Whew. That's part 2. So we have one part left, one section left before we're done with this course. This chapter. There's lots to learn in statistics. And we're going to do linear equations and regression next. How we get that regression line with which we test our correlation coefficient with. So yeah, make sure you keep practicing. Review these videos and the lecture slides. If you're stuck, again, you could teach yourself this. If you're good at statistics and math, great. If you're not, use these resources, videos, guides to help you. Practice your questions on the worksheet. I'm just showing you the answer one right now. But again, there is a one without the answers. At this point, you should be able to answer questions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Yep, all the way up to question 14 at this point. And then there's still a few more questions afterwards. 4 more. But yeah, this is a good time, if you haven't already, to start practicing on your practice worksheets. So again, if you got any questions, you can ask me via email or Canvas messages, or leave a comment in the YouTube video if you watch that. Not getting many views, that just tells me you haven't watched these yet. Maybe in the future classes where this is online, it would be a case. But in your case, yep. The more you do, the more you practice, the more this will stick for anybody. So we're here to help you out. Ask me if you got any questions, and we'll see you in the next one.